Welcome students to the MOOCs series of lecture on statistical inference. This is lecture number 17. Over the last few classes, we have been discussing theory of estimation. In particular, we have discussed desired properties of an estimator, namely unbiasedness, consistency, efficiency, sufficiency, which we expect in a good estimator to have. But the main question is how to find an estimator. Suppose we have x 1, x 2, x n as samples from our distribution f x theta, or I may write f theta of x, where theta is the parameter of the distribution. And we know that theta belongs to capital theta, the parameter space, for example, Bernoulli P, P belongs to 0, 1. Now, we can have estimator of two types. One is point estimation or point estimator, in this case we try to obtain a single value for the unknown parameter theta. And the second one is interval estimation, where we try to obtain an interval such that theta belongs to this interval with certain degree of confidence. For example, we have tossed a coin, say 10 times, and suppose the outcomes are head, tail, 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 head, head, tail, tail, head and tail. So, we can compute x bar is equal to sample mean is equal to 4 divided by 10, 4 comes because there are 4 successes, is equal to 0.4. And we know that sample mean is an unbiased estimator. Sample mean is unbiased for p. Therefore, our point estimation of p is equal to x bar is equal to 0.4, and we often denote it as p hat, where p hat is an estimated value of the unknown parameter p. But if we think realistically, just because we got 4 heads out of 10 tosses does not imply that p is equal to 0.4. In another set of experiments, you may get with the same coin different values of p hat. So, often we may like to present the result in the form of an interval. Say for example, if we get 4 heads out of 10, we may say the actual value of p will lie in say 0.35 to say 0.55. So, we are giving an interval and we are saying that the value of the parameter will lie in this interval with certain degree of confidence, say 95% confidence. When we present the result in this manner, we call it an interval estimation of the parameter. In the present talk, I will be discussing point estimation primarily. There are many methods but the two most important ones are method of moments and method of maximum likelihood. So, in this talk I will be discussing these two methods in detail. So, method of moments. Suppose our theta is not a real, rather a vector of more than one parameter. For example, normal mu sigma square has two parameters. Similarly, gamma alpha beta has two parameters. So, if we have theta is equal to a k dimensional vector theta 1, theta 2 up to theta k, then to estimate theta, or say theta I is equal to 1 to k, we form k equations with the help of sample raw moments. Where the rth moment is sigma x to the power r f x dx. This is the rth raw moment. Then, by computing m1 prime, m2 prime up to mk prime, and obtaining their equations by equating them with the sample moments, which will involve theta 1, theta 2 up to theta k, and solving these k equations, we get theta 1 hat, theta 2 hat, theta k hat. So, let me give you an example. Gamma, lambda, alpha. We need to estimate lambda and alpha. So, what we have done? We have taken say n samples from the population. Then what is the first moment? The first moment is equal to mu 1 prime and we know that for gamma it is expected value of x is equal to alpha upon lambda, and the second moment is equal to mu 2 prime is equal to expected value of x square is equal to 0 to infinity x square lambda power alpha upon gamma alpha e to the power minus lambda x, x to the power alpha minus 1 dx is equal to 0 to infinity x square lambda power alpha upon gamma alpha e to the power minus lambda x, x to the power alpha minus 1 dx, which is equal to 0 to infinity lambda power alpha upon gamma alpha e to the power minus lambda x, x to the power alpha plus 2 minus 1 dx. And we know that this is going to be lambda power alpha upon gamma alpha into gamma alpha upon lambda power alpha plus gamma alpha plus 2 upon lambda power alpha plus 2, which is equal to alpha into alpha plus 1 gamma alpha, this part is equal to alpha into alpha plus 1 times gamma alpha into lambda square into lambda power alpha. Therefore, after cancellation we have mu 2 prime is equal to alpha into alpha plus 1 upon lambda square. Suppose now from the sample we calculate sigma xi by n, where n is the sample size, and call it m 1 prime, and sigma xi square by n and call it m 2 prime. Then we can write m 1 prime is equal to alpha over lambda and m 2 prime is equal to alpha into alpha plus 1 upon lambda square. Therefore, m 2 prime upon m 1 prime square is equal to alpha into alpha plus 1 upon alpha square, as this lambda square will get cancelled. Therefore, m 2 prime upon m 1 prime square is equal to alpha plus 1 upon alpha. Therefore, alpha m 2 prime is equal to alpha plus 1 m 1 prime square, or alpha times m 2 prime minus m 1 prime square is equal to m 1 prime square. Therefore, an estimate of alpha is equal to alpha hat is equal to m 1 prime square upon m 2 prime minus m 1 prime square. Therefore, since we know that alpha upon lambda is equal to m 1 prime, therefore, lambda upon alpha is equal to 1 upon m 1 prime. Therefore, lambda hat is equal to alpha hat upon m 1 prime, where alpha hat we have found from here, and that cancels 1 m 1 prime. Therefore, lambda hat is equal to m 1 prime upon m 1 m 2 prime minus m 1 prime square. Thus, by equating the sample moments with the parametric equations, and solving them, we get the estimates. Consider another example. Suppose we want to estimate alpha and beta, the parameters of beta 1 alpha beta distribution. Again, let us consider mu 1 prime, zero to 1 x 1 upon beta alpha beta x to the power alpha minus 1 1 minus x to the power beta minus 1 dx is equal to gamma alpha gamma beta upon gamma alpha plus beta. This I have taken out, multiplied by integration 0 to 1 x to the power alpha plus 1 minus 1 into 1 minus x beta minus 1 dx. This is equal to gamma alpha plus beta upon gamma alpha gamma beta into 0 to 1 x to the power alpha plus 1 minus 1 1 minus x whole to the power beta minus 1 dx. And this integral gives us beta with alpha plus 1 and beta as their parameters. Therefore, this is equal to gamma alpha plus beta upon gamma alpha gamma beta multiplied by gamma alpha plus 1 gamma beta gamma alpha plus beta plus 1. This is equal to this cancels, and we know that gamma alpha plus 1 is equal to alpha times gamma alpha. So, that cancels this gamma alpha with this, and we are left with alpha. In a similar way, this is equal to alpha plus beta into gamma alpha plus beta. So, this gets cancelled and we are left with alpha plus beta. Therefore, the sample moment can be equated sample first moment can be equated with alpha upon alpha plus beta, or alpha upon alpha plus beta is equal to m 1 prime. So, this is the first equation. In a similar way, we can calculate mu 2 prime, which is the expected value of x square. So, what it is? This is equal to integration 0 to 1 x square 1 upon beta alpha beta multiplied by x to the power alpha minus 1 minus x to the power beta minus 1 dx. This is equal to, as before, gamma alpha plus beta upon gamma alpha gamma beta into 0 to 1 x to the power alpha plus 2 minus 1 minus x beta minus 1 dx. This is equal to gamma alpha plus beta upon gamma alpha gamma beta multiplied by, now this is giving us beta with alpha plus 2 and this beta. So, we have gamma alpha plus 2 gamma beta upon gamma alpha plus beta plus 2 is equal to gamma alpha plus beta gamma alpha gamma beta into, now gamma alpha plus 2 is equal to alpha plus 1 into gamma alpha plus 1, which again is alpha into gamma alpha. So, I can write it as alpha into alpha plus 1 into gamma alpha, then gamma beta, and this is alpha plus beta plus 1 into alpha plus beta into gamma alpha plus beta. So, after cancellation we will have alpha into alpha plus 1 upon alpha plus beta into alpha plus beta plus 1. Therefore, we have alpha upon alpha plus beta is equal to m 1 prime, which is the sample mean, and alpha plus 1 upon alpha plus beta into alpha plus beta plus 1 is equal to m 2 prime, which is sample mean of x square. Then we can solve these two equations and obtain estimated value of alpha hat and beta hat as estimators for alpha and beta respectively. Similar equations can be formed with other distributions, and one can obtain the estimates through the method of moments in the above way. Now, let me discuss maximum likelihood estimators or estimation. In short, we will write it as MLE. The idea is as follows. Suppose we obtained x1, x2, xn as our sample values from f theta x. Then the likelihood function of this sample is defined as L theta of x1, x2, xn is equal to the joint density of x1, x2, xn, and if the samples are independent, it is product of f theta of xi, I is equal to 1 to n. We have already seen the likelihood function when we are discussing Cramer-Rao inequality. So, this is not something that is new to us. The idea of likelihood estimation is that we try to obtain that particular value of theta which maximizes the probability of occurrence of the sample x1, x2, xn. So, the MLE for theta is that value of theta that maximizes the probability of occurrence of the sample x1, x2, xn. So, how to obtain that? Therefore, we differentiate L theta of x1, x2, xn with respect to theta and equate that to 0. From this equation, we solve for the estimated value of theta. Of course, when we are solving the equation del L del theta is equal to 0, we also will have to see that the second order derivative is negative. Then only we can ensure that this solution theta hat is actually giving us the maximum probability for the obtained sample x 1, x 2, x n. Note, often instead of del theta of L theta of x 1, x 2, x n, for computational ease we differentiate log of L theta of x 1, x 2, x n, and since log is an increasing function, the result is not altered. So, let me give you an example. Consider Bernoulli P. Therefore, x 1, x 2, x n are sampled values. Therefore, log of x 1, x 2, x n is equal to, we have already seen this is p to the power sigma x I into 1 minus p whole to the power n minus sigma x I. Therefore, log n, therefore, log L x 1, x 2, x n is equal to sigma x I log p plus n minus sigma x I log of 1 minus p. Therefore, del log L del p, because here the parameter is p, we could write theta is equal to p or theta is equal to p. Therefore, del log L del p is equal to sigma x I upon p plus n minus sigma x I upon log of 1 minus p is equal to 1 upon 1 minus p multiplied by d 1 minus p dp, which will give you minus 1 is equal to sigma x I upon p minus n minus sigma x I upon 1 minus p. So, this is star. I will need it later when I will be considering the second derivative, but to obtain the value for which log L is maximum, that is L is maximum, we equate sigma x I upon p minus n minus sigma xi upon 1 minus p is equal to 0. Or sigma xi into 1 minus p is equal to p times n minus sigma xi, or sigma xi minus p times sigma xi is equal to n p minus p sigma xi. So, this cancels, or p hat is equal to sigma xi upon n is equal to sample mean. Therefore, from here also we find that if we consider p hat to be the sample mean, then we get del log L del p is equal to 0. Therefore, x bar can be a possible solution, provided if del 2 log L del p square, because theta is equal to p, is less than 0. We already had del log L del p is equal to this. So, now we are differentiating this with respect to p. Minus sigma xi upon p square minus n minus sigma xi upon 1 minus p whole square. This will be multiplied by minus 1. So, that will make it plus 1, because 1 minus p whole to the power minus 1 was there. This multiplied by d 1 minus p dp, which like in earlier case is going to be minus 1. Therefore, del 2 log L del p square is equal to minus sigma xi p square minus, now this minus again makes it minus n minus sigma xi upon 1 minus p whole square. Since sigma xi can maximum value be n, therefore, n minus sigma xi is positive. With this negative sign, this becomes negative, this becomes negative, this is positive, this is positive. Therefore, the whole thing is less than 0. Therefore, MLE for p is equal to x bar. Let us now consider normal mu sigma square of x. Therefore, f x is equal to 1 over root over 2 pi sigma e to the power minus 2 sigma square into x minus mu whole square for minus infinity less than mu less than sigma less than infinity. Therefore, L of course, mu sigma square, which we often write as L theta, is equal to 1 over root over 2 pi sigma whole to the power n e to the power minus 1 upon 2 sigma square sigma xi minus mu whole square. Therefore, log L is equal to minus n log root over 2 pi, this is from here, minus n log sigma minus sigma xi minus mu whole square divided by 2 sigma square. Or if we write it with sigma square as the parameter, if we write sigma square as the parameter, then we can write log L is equal to minus n log root over 2 pi minus n by 2 log sigma square minus sigma xi minus mu whole square upon 2 sigma square. Therefore, del log L del mu is equal to, this gets cancelled because this gives 0, this gives 0, and what we are left with is minus 2 into sigma xi minus mu. Now, this is with minus sign, so that makes it plus upon 2 sigma square is equal to sigma xi minus mu upon sigma square, and del log L del sigma square is equal to from here we are differentiating it with respect to sigma square. Therefore, log of sigma square derivative is 1 upon sigma square. So, what we are getting is minus n upon 2 sigma square, and from the other one we are getting plus sigma xi minus mu whole square upon 2 into 1 upon sigma square whole square. Because if you look at this, it is 2 sigma square. So, sigma square to the power minus 1. So, when we are differentiating, we are getting that minus will make it plus and 1 upon sigma square whole square. Therefore, To solve them, we need to equate the partial derivatives with 0. From equation 1, we have minus xi minus mu upon sigma square is equal to 0. Therefore, sigma xi minus n mu is equal to 0. Therefore, mu hat is equal to sigma xi upon n. So, that is the estimate for mu. From the second equation, which is minus n upon 2 sigma square plus sigma xi minus mu whole square upon 2 sigma square square is equal to 0. We get sigma xi minus mu whole square upon 2 sigma square square is equal to n upon 2 sigma square. So, this cancels, one of these cancels. Therefore, sigma square hat is equal to sigma xi minus mu whole square upon n, but we do not know mu, we know only mu hat. Therefore, sigma square hat is equal to sigma xi minus x bar whole square upon n. So, that is the maximum likelihood estimate for sigma square, and we already knew that this is not an unbiased estimator, because the unbiased estimator for sigma square is sigma xi minus x bar whole square upon n minus 1, when the mu is unknown to us. However, MLE gives us this to be the estimator. कितना टाइम है? बीच में से थोड़ा सा काटेगा, मैं 1-2 मिनट में और कुछ बोल के इसको ख़त्म करता हूँ. Sometimes the above trick or above scheme does not work. For example, consider uniform alpha beta. Therefore, log is equal to for uniform alpha beta, f x is equal to 1 upon beta minus alpha. Therefore, the likelihood function of x 1, x 2, x n is equal to 1 upon beta minus alpha whole to the power n, and this does not give us any solution. Therefore, log L is equal to n log beta minus alpha with a minus sign. Therefore, del log L del alpha is equal to minus n upon beta minus alpha, and now make it plus, and del log L del beta is equal to minus n upon beta minus alpha. By equating 0, by equating with 0, we get beta minus alpha is equal to infinity. Therefore, that does not give us a solution. What we can do in the following way, we need to check when beta minus alpha is minimum. In that case, L is equal to 1 upon beta minus alpha whole to the power n will be maximum. Now, alpha has to be less than equal to x 1 and beta has to be greater than equal to x n. This is the first order statistics, this is the nth order statistic. Therefore, beta minus alpha is minimum if beta is equal to x n and alpha is equal to x 1. Therefore, x n is the beta hat and alpha hat is equal to x n. These are the MLE for alpha and beta. Okay. With that, I stop here today. In the next lecture, I will give you some properties of maximum likelihood estimator, and also I will talk about interval estimation. Thank you.